This is video lesson number 4 in the optics series. This is the first lesson on refraction. So refraction is the bending of light as it passes from one medium to another. So a medium is some type of substance. It could be air, it could be water, it could be glass, it could be plastic, it could be quartz, anything that light can travel through. So refraction is the bending of light as it passes from one medium into another. Now you may have noticed if you were to put a straw or a spoon in a cup of water that there's a bit of a distortion to the image, or if you drop something into a pool, it looks like it's closer to you than it actually is. And those differences in the way something looks is due to the bending of light as it travels at different speeds through different media. So this occurs because the speed, of the light changes when it passes from one medium to another. The speed of light is different in different media. Because different media have different what we call optical densities. And that basically has to do with the type of particle that the medium is made out of, how close the particles of that media are together, and how much they sort of interfere with the light being able to travel in a straight path through the substance. So in a vacuum, if you had a completely empty area, the light can travel directly through without being impeded whatsoever. But if you have something that's more optically dense, like water or glass, you have particles within that make up that particular media, and light always travels in straight lines. But it bounces off of stuff when it touches it. So when the light comes into the media, it might hit one of those particles and bounce around a little bit before it comes out on the other side. And while this is a very zoomed in version, and so overall, when you look at it, it looks like it's going in a straight line. Because it's kind of bouncing around a little bit within the media, its overall speed from when it enters to when it exits that media is slower than what it would be in a vacuum. Now, light is technically always traveling at the speed of light, but it's just that it's taking a longer path, so overall it takes more time to get from one end to the other. So the speed of light, the way we talked about it before, we said that c was the speed of light in a vacuum, and it was 3.0 times 10 to the power of 8 meters per second. So this symbol is c, the unit is meters per second, and that is speed of light in a vacuum. We often use that as the speed of light through air as well, because the particles in air are so far apart from each other that light is traveling almost at that same speed. But the speed of light in a particular medium, depends on the optical density of that medium. So we use a different letter to show the overall speed of light through a particular medium. And this is where we're going to come back to that letter V that we talked about in the first lesson. And it's still going to be meters per second. It just might not always equal the constant value c, which is speed of light in a vacuum. So the more optically dense a media is, the slower the light is going to travel overall through that medium. So with increased optical density, we have decreased speed. So how do we measure this? We measure this using something called the index of refraction. So it's a measure of optical density okay, of a medium as a ratio to the optical density of a vacuum. So if you look at the table to the side, you'll see vacuum has an index of refraction of 1. So at sort of max speed in terms of how the light is traveling, okay, it's going to go at 1 for the optical density of being completely empty, no particles to interfere with. But as you see, if you get more and more optically dense materials, okay, that number goes up as a ratio of how quickly the light can travel within that particular media compared to how fast it can travel within a vacuum. So the symbol for the index of refraction is n, so lowercase n, and it has no units. Okay, because it's a ratio, it's a comparison of meters per second to meters per second, which when you divide anything by itself, it just goes away and becomes nothing. So there's no units for that one. There are two ways we can calculate the index of refraction. Okay, so the first one is looking at a ratio. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction. Okay, this is called Snell's law. So our formula is n equals sine theta I over sine theta r. So the angle of incidence over the angle of refraction. Now, what are these things? Let's go back a page for a moment and label them on our diagram so that we know what we're talking about. Before, when we were talking about angles of incidence and reflection, okay, we were only working on one side of a completely reflective surface where none of the light was transmitted. It was all bouncing off of like the mirror or whatever it might be. So this is our incident ray. Okay, this is our reflected ray. And this one here is our refracted ray. So often substances will be somewhat be able to transmit light, but will also reflect light. So if you think about water, if you were to look at water, some light is reflected back at you and some light passes all the way through. Okay, so and that's the same with glass. If you ever see, you know, a slight reflection of yourself in a window, but you can still also see outside. That's an example of when you have some light being reflected and some being refracted. Remember that this dashed line we call normal. Okay, and we measure all of our angles to normal, not to the surface of your medium. So our angle of incidence, okay, was between the incident ray and the normal, and our angle of reflection, which is theta lowercase r, is measured between the normal and the reflected ray. Our new piece here is looking at the angle of refraction, which is measured between the refracted ray and normal. And we call it theta capital R for the refracted ray. So when you're doing calculations of Snell's law, so our sine theta I over sine theta r to find the index of refraction, okay, these are what those angle measurements are going to be. So sine theta I is going to be sine times whatever that degree is over sine theta r is that one. The other way you can calculate the index of refraction is by looking at the ratio of the speed of light in a vacuum compared to the speed of light in the medium you're looking at. And for that, our formula is n equals c over v. So where c is the speed of light in a vacuum, okay, which is that 3.0 times 10 to the power of 8 meters per second, and v is the speed within the medium. So overall, to kind of summarize here, we've got an increase in optical density means you're going to have a higher index of refraction. And that's going to mean a lower overall speed of light through that medium. Okay, so we've got a few example questions here. So example number 1, light passes from air into a plastic prism. If the angle of incidence is 37 degrees and the angle of refraction is 22 degrees, what is the index of refraction for the plastic prism? So we'll start by writing out everything that we know. N is index of refraction. We don't know what that is. That's what we're looking for. Because we're given two angles, we're going to be using Snell's law for this question. We're given that equation there. So theta I, your angle of incidence, is 37 degrees. And theta R, angle of refraction, was 22 degrees. So now we can put our equation in. N equals sine theta I over sine theta R, which equals sine of 37 over sine of 22. Now the way that we type that into our calculators, because you guys may not have done this before, because you would have done this in math class before doing it in regular grade 10, but because this is the summer course, you haven't necessarily seen sine before. So on your calculator, okay, you'll notice that there are some buttons that say sine, cos, tan, and like different things along the top. So your sine button is this one. So when you turn your calculator on, you want to make sure it's in degrees. So there should be a little D somewhere on it to show that you're in degrees. Oops, go back. So we're going to type in bracket sine 37 divided by sine 22 equals 1.6065 blah, 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 blah. We're not going to learn about significant figures in this course, so I would recommend that you keep maybe 2 decimal places as just kind of a standard rule of thumb for this class. So I'm going to round that to 1.61. And I want to quickly talk about why this makes sense. So plastic prism, okay, looking over here at some of the other things, you've got things like sapphire and glass are kind of all around that same area. So this number of being 1.61 kind of makes sense in terms of it's greater than 1, but it's not like massive like something like diamond. If you ever get an index of refraction that's less than 1, then you've made a mistake in your calculation somewhere, because you can't have something that has an index of refraction less than the vacuum. Okay, it has to be a number greater than 1. And it's usually 1 point something, and it's usually probably less than diamond most of the time, 1 point something. So that can kind of help you figure out whether your number makes sense or not. So we can finish this off with a therefore statement. Therefore, the index of refraction, remember there's no unit on that, it's just a number, for the plastic prism is 1.61. Let's try a couple more. The speed of light in a sample of glass is 1.91 times 10 to the power of 8 meters per second. What is the index of refraction for the glass? So here we're given a speed of light through a specific medium. So looking at your equations, we're going to be using this equation, the speed of light equation, because we're given V, and we know that C is always a constant. It's always that 3.0. So we can use this one versus we're not given any angles, so we can't complete that we can't complete the Snell's law equation. So let's write down what we know first. C equals 3.0 times 10 to the power of 8 meters per second. So speed of light in a vacuum. Comparing that to the speed of light through this particular medium was 1.91 times 10 to the power of 8 meters per second. And N is what we're looking for. Our equation is N equals C over V. So we can sub our numbers in. 3.0 times 10 to the power of 8 meters per second divided by 1.91 times 10 to the power of 8 meters per second. Okay, when you type that into your calculator, make sure you're doing scientific notation correctly. If you're having any trouble with that, please reach out to me and I can help you figure out how to do it properly on your calculator. This is going to give us 1.57 as our index of refraction. So therefore, the index of refraction of this glass is 1.57. Now the next question says, what is the speed of light in water? For this one, we're going to need to look at that table on the previous page. So here we're still using this equation because we know C and we can find N by using the table, and we're going to be solving for V this time. So on our index of refractions table, pure water has an index of refraction of 1.33. So we'll write that down. N of water is 1.33. We also know C is 3.0 times 10 to the power of 8 meters per second. And V is what we don't know, but we know that it will be measured in meters per second because it's a speed. Our equation, N equals C over V. When you're solving for V, okay, you can rearrange V equals C over N. If you want to make it into a magic triangle, you can do it that way. So you'd have C, N, and V there. And then we're going to sub in our numbers. So 3.0 times 10 to the power of 8 meters per second divided by 1.33. That's going to give us 2.26 times 10 to the power of 8 meters per second. Now, you'll notice that here I'm getting times 10 to the power of 8. That's what most will be. So most speeds of light, okay, aren't going to be as big as 3, but they're still going to be on the same magnitude or close to it. You're not going to get a number like 5. Okay, that will not happen. It has to be like kind of on the same order because light is going to be traveling extremely fast. It's not like it's only going to be going 5 meters per second. The biggest mistake that people make is they rearrange this equation incorrectly and they multiply C times N rather than dividing. And what happens with that is you're taking your 3.0, you multiply it by 1.33, you're going to get a number greater than 3.0 times 10 to the power of 8 meters per second. And nothing can go faster than the speed of light in a vacuum. You should never ever get an answer for a question like this, okay, that is greater than this number, because it can't travel faster through glass than it can through air, vacuum. Like that's just not possible. So make sure you're doing the rearranging of your equation correctly. So here's our final speed. So we can add our therefore statement. Therefore, the speed of light in water is 2.26 times 10 to the power of 8 meters per second. Now there's some practice questions on this page and the next page for you to do and submit for practice. But I'm going to keep going here and do page 22 because it will help you with answering this question a little bit. So the final piece here, when we're looking at refraction, okay, so light refracts only at the boundary, okay, as it enters a new medium. So it's not going to continue to change and bend throughout the medium. The change is instantaneous at the surface, like that exact moment where you switch from one medium to another, and then it's going to travel in a straight line again. So to give an example, okay, if we look at this and we say that this is a piece of glass and this is, so we'll say this is air and this is glass. We're going to start with a ray coming in and hitting the glass. So it's coming in from the air. There's our angle of incidence. Okay, and it's going to hit the glass and it's going to slow down. Now, when something slows down, it's going to actually bend towards the normal line. Okay, so light slows down because this is more optically dense. So light slows down when it passes into a more optically dense medium, okay, and it bends towards the normal. So if I was going to sketch this, I want to make sure that my angle of refraction is smaller than my angle of incidence. You don't have to measure a specific angle with like a protractor or anything, and we can exaggerate this a little bit to make it clear. But theta r, as long as it's visibly smaller than theta I, if it's going into a more dense medium, then that's good. Now, the only problem with this diagram is that this box is only going to here. So really kind of, I should only draw the line to there, and then it would bend again when it leaves that piece of glass. But just for the sake of the diagram, I'm only going to show one. In the second one, let's go the other way around. So now if we're starting in the glass, we're going towards the air. So from more optically dense into less optically dense. Our incident ray is coming in through this dense material with an angle of incidence. And when it hits the air, okay, it's going to speed up because the air is less optically dense. So light speeds up when it passes into a less optically dense medium, okay, and it bends away from the normal line. So what that means is my angle of refraction needs to be larger than my angle of incidence this time. So again, thinking about it coming from your normal line, my angle of incidence is about that big, so I'm going to make sure that my angle of refraction looks bigger than my angle of incidence. So you're going to do a couple more of these practice as well. So on page 22, you have a couple of examples to practice this type of diagram. You can set it up as having a normal line down the center. So I'll set one up for you so you can see how to do it. Then you want to draw your boundary line. So across the center, you're going to draw a straight line and you're going to label which is which. So this is light moves from sapphire into water. So I might label this as sapphire and this as water. And it's helpful to put in your index of refraction right into the diagram. So to find the index of refraction, you're going to go back to page 19 and look it up on the table. So sapphire is 1.77. So n equals 1.77. And water was 1.33. So n equals 1.33. Okay, when you read the question carefully, it says moves from sapphire into water. So I'm starting at sapphire. I'm going to start by putting in an incident ray and an angle of incidence. So this is my incident ray and my angle of incidence. And you're going to have to predict over here with the water, is it going from less dense to more dense or more dense to less dense? How is that light going to bend in this medium? And then another example on B. The answers to these two will be posted. You don't need to submit this page, but just check your work.